Hey there, this is Alberto, and in this video I will teach you to code a fully convolutional network. A cutting-edge model that achieves state-of-the-art in tasks like semantic segmentation by taking advantage of three special techniques. 1. Replace fully connected layers with one-by-one convolutional layers. 2. Observing through the use of transposing convolutional layers. 3. Ski connections. This allows the network to use information from multiple resolution scales. So let's see how to translate this into code.
First, we need to import the package that we need. Structurally, an FCN is composed of two parts, an encoder and a decoder. The encoder is a set of convolutional layers like VGG or ResNet, and is used to extract features from the image. In this case, I will use VGG 16. So I have my cross encoder that inherits from VGG, from transmission, and I had some optional parameters, like if I want it to be pre-trained, if I require gradients. If this is false, then I will freeze the encoder and I will only train the decoder part. First, normalization, if I want to add normalization layers to the encoder. And show params, that is a function to see the dimensionality of the encoder. So the constructor is called, it will use the main layer function to create architecture. This is a copied function from Pytorch, so I will leave a link below in the description, but this just create architecture. So let me show you. And from Torch Vision import models, model is equal to models dot VGG 16, and I will print the model. Here we can see that we have three parts. The first is the feature expressions. This is the set of convolutional layers that we are interested in. Then we have an average pool and a classifier. We will remove this classifier, and I do this with this line of code in the constructor, del self.classifier, to remove this part. And I build this in this way because of this function, the forward function. This will help me to extract the output or the max pooling layers, and this will help us to create the ski connections. So I define range, like for example 0 to 5, and this represents the location of the max pooling. So for example here, 0, 5, if we return to the architecture, we will see that 0 to 5. The layer number 4 is a convolutional, but the layer before is a max pool. So I am taking this layer, I am taking the output of this layer. Same with the others. I will take the output from the layer 9th, 16th, 23, and 30. This is 9, 16, 23, and 30. This is the last one. Here, the network is processing the image through all the entire network, but when it reaches a max pooling layer, it says the output in a dictionary called output, and this dictionary is what I will return to the decoder. So as a quick overview, we created the architecture of VGG, we removed the classifier, and we extracted the output of the max pooling layers, so we can create the ski connections. This is the encoder part. So let's move to the decoder part. Now we need to define the decoder part. The decoder's goal is to scale the output of the encoder such that it's the same size of the original image. So I have this crash decoder that inherits from module as all the deep learning architecture that you created in Pytorch, and it takes as input the encoder or VGG and then crosses. This is the number of crosses that you want to classify. So this is the first layer, the con1, and it represents the one-by-one convolution. It takes int a number of filters and returns the same number of filters. So we have 512. How I know this number? Well, if we return to the encoder part, we will call this and we will show the params. We'll say model is equal to encoder is equal to encoder and show params equal true. This is the dimensionality of the encoder, and as we can see here, it returns 512 feature maps. This is how I know that we return 512 feature maps as the input for the decoder. After that, we have batch normalization layers. This will speed out the training process by standardizing the output of each layer. And more convolutional transport layers. This is essentially a reverse convolution where the forward and backward processes are swept, and they help to upsample the previous layers. And finally, we have the convolutional score layer. The kernel is equivalent to the number of outputs, and this score layer represents our semantic image. This is the tensor that the network will return, and this is the architecture for the decoder. After that, we need to define its behavior in the forward function. First, we send the input to the encoder to extract the image features and the outputs of the max pooling layers. Pool file represents the output of the VGG network, so it is the input for the decoder part. Here we have the first ASCII connections by adding pool 4 to the output of the first layer. Here we have another ASCII connections, adding pool 3 to the output of the second layer of the decoder. And then we just enter the input to the rest of the layers until we get our output tensor, and that is basically our forward method. So as a quick overview, we have the architecture. The architecture is to sample the previous layers. We create the ASCII connections and return a tensor that represents our semantic image. So let's go to the part of testing. In this part, we will create our model, FCN, which is the decoder that takes as input the VGG and the number of crosses. So I am saying that I have 12 crosses, I have a batch size of 10, and my image has dimensions of 2024 by 2024. It should return a tensor with the dimensions of batch size and crosses and the same width and the same height that we had. So let's run this. As you can see, it works, but it is a fixed network because of the dimensionality of the VGG. So this can take images of any width or any height that are multiples of 32. So I got 32 here, we'll say 56, 56. It should work too. As you can see, it works too. Also, I modify again the width and height, and I use a high width and a high height. It will work because it is multiple of 32, and it works. But what happened is I modified and then I changed the size for 500 by 500. This should return an error. This error is a dimensionality error of the VGG. As a crew, you can print the size of this and you will see what caused the error. So yeah, we have a fixed FCN. It works for multiples of 32. If we want it to work for any size, then we must modify the VGG architecture, and we just return to the values that we had before. So 24 by 24, 24 by 24. And yeah, this is the FCN, a fixed FCN. And also I will leave you the link to the code in the description. And if you want to operate this and make something like this, well, I will leave you the link in the description too.
You have learned how to code a fixed FCN. The main difference between a normal convolutional neural network and a fully convolutional network is that this last preserves the spatial information throughout all the entire network. And I said a lot the word network. Subscribe. Bye. Cutting edge technology.